These are the full solutions to the 2008 AP Chemistry exam. You should go to the AP Chemistry website at collegeboard.com to download and print a copy of the exam to use with this video. 1. We write down the equation and some of the relevant data from the table given in the problem. A. We see that carbon here is a solid, so its partial pressure or concentration does not enter the equilibrium constant. Kp is the equilibrium constant in terms of partial pressures. Kp equals the partial pressure of CO squared divided by the partial pressure of CO2. B. At the beginning, before equilibrium is reached, the total pressure is 5.00 atmosphere. The problem says that there is only CO2 initially and some solid carbon, but no product. So the entire 5.00 atmosphere is CO2 gas. We use the ideal gas law, PV equals nRT. N equals to PV divided by RT. Putting in the numbers, P equals 5.00 atmosphere, V equals 2.00 liter, R equals 0.0821 liter atmosphere per mole per K, and T equals 1160 K. We can calculate N, which comes up to be 0.105 mole. C. The problem says that at equilibrium, the CO2 partial pressure is 1.63 atmospheres. The data in the table indicates that after a certain time, the total pressure no longer changes. Going from 8 hours to 10 hours, it seems that the system has reached equilibrium. Therefore, the equilibrium total pressure of the system is 8.37 atmospheres. The equilibrium mixture contains only two gases, CO2 and CO. Therefore, we can compute the CO partial pressure, which is a total 8.37 atmosphere, minus the CO2 pressure, which is 1.63 atmosphere. It comes up to be 6.74 atmosphere. To compute the value for Kp, we plug these two partial pressures into the equilibrium expression. We get 27.9. D. Adding a catalyst will not change the equilibrium constant or the equilibrium position. It will only help the system reach equilibrium faster. The final equilibrium mixture must be the same with or without the catalyst, and the total pressure should also not change. E. In another experiment, we have initial pressure of both CO and CO2 equal to 2.00 atmosphere at the same temperature. The mass of carbon and the volume given are irrelevant for Kp. Only the partial pressures of CO and CO2 are important. To see if the system is at equilibrium, we compute the reaction quotient Q. Q has the same expression as K, except we use the initial partial pressures. We see that Q comes out to be 2.00, which is less than Kp. An easy way to remember how to determine the direction of the reaction is we put K and Q on the number line, and we see that Q is on the left side of Kp. Therefore, in order to reach equilibrium, the reaction has to proceed to the right. Since CO is the product, the reaction must produce more CO. Two, let's write down the equation first. Sometimes when an ionic compound crystallizes from a solution, it can incorporate some water molecules into the solid. These water are called hydration water. When hydrated MgCl2 is heated, you can drive off the hydration waters. We reproduce the data from the table given by the problem. A. If you heat the hydrated MgCl2, it will eventually lose all of its hydration water, and the mass decreases because water is lost. We see that between the second and the third heating, there is no additional mass decrease. Therefore, the sample seems to have lost all of its hydration water already. B. The mass of water lost is the difference between the initial mass of the container plus the hydrated sample and the dehydrated sample plus the container at the end. So it is 1.848 grams. To compute the number of moles corresponding to this, we need the molar mass of water. Dividing the mass by the molar mass, we get 0.1026 mole of water. To compute the coefficient n, we must also know the number of moles of MgCl2. The ratio of the number of moles of water to MgCl2 should give us n. To compute the number of moles of MgCl2, we need this mass. This is given by the difference between the dehydrated MgCl2 plus the container and the mass of just the container itself. This comes out to be 1.630 grams. We need the molar mass of MgCl2. From these, we can calculate the number of moles of MgCl2, which is 0.01712 mole. We take the ratio of the number of moles of MgCl2 to that of water, which is 0.01712 to 0.1026. If we divide both numbers by the smaller of the two, we get approximately 1 to 6. Therefore, the formula of dehydrated MgCl2 should have N equals to 6 water molecules in it. C. If some additional mass is lost due to an error, the total mass at the end is smaller than it should be. The mass of the water lost calculated from the final mass minus the empty container would have come out too large. D. To obtain the mass of the AgCl precipitate, the easiest steps are: 1. Filter the solid AgCl from the solution. Two. Wash and dry the filtrate. And 3. Weigh the dried sample to determine its mass. E. The problem says that the mixture contains a total of 2.94 grams. When this mixture is dissolved in water, everything dissolves because both MgCl2 and KNO3 are soluble. The solution therefore contains Mg2+ ions, Cl-, K+, and NO3- ions. While Ag+ ions from silver nitrate is added to the solution, the Ag+ and Cl- will form a precipitate. The Cl- that end up in this precipitate all came from the MgCl2. Determining the number of moles of Cl- will therefore give us the number of moles of MgCl2 originally in the mixture. The mass of the AgCl precipitate is 5.48 grams. We need the molar mass of AgCl. The number of moles of AgCl is 0.0382 mole, and this is equal to the number of moles of Cl- ions. Because in each MgCl2 there are two Cl-, the number of moles of MgCl2 in the original mixture must be half of this, which is 0.0191 mole. The mass percentage of MgCl2 is the mass of the MgCl2 divided by the total mass of the mixture times 100%. The total mass is 2.94 grams. We need the mass of MgCl2. We already know its number of moles. If we multiply this by the molar mass of MgCl2, we should get its mass. The mass of MgCl2 is 1.82 grams. Therefore, the mass percentage of MgCl2 is 61.9%. 3. We will first write down the equation. The overall potential is plus 0.62 volts. A. The problem gives you the two half reactions. The half reaction potential for the second one is unknown. To get the overall reaction above, we see that Cu on the reactant side is on the right side of the first half reaction. Therefore, we must flip this around and reverse the sign of the half reaction potential. We now see that the first half reaction transfers 2 electrons, but the second one transfers 3. To make sure the same number of electrons are exchanged, we must multiply the first half reaction by 3 and the second half reaction by 2 to get a total of 6 electrons exchanged. However, it is important to remember that you never have to multiply the half reaction potential by the stoichiometric coefficients. Therefore, the overall potential is 0.34 volts plus the unknown potential of the second half reaction. The total is 0.62 volts. Therefore, the potential of the second half reaction must be plus 0.96 volts. B. The relationship between the reaction free energy and the overall potential is delta G0 equals negative N times F times E. N is the number of electrons exchanged, which we see from above is 6. F is the Faraday's constant. The answer should come out in joules per mole. So the answer is negative 360 kilojoules per mole. C. We need to estimate the sign of delta S. We know that gases have much larger entropy than solids, liquids, or solutions. The reaction is 2 moles of gases on the product side, but none on the reactant side. The rest are solids, liquids, or solutions. Therefore, the product side should have higher entropy, and delta S must be positive. D. The second part of this problem is about the reaction between NO and O2 to make NO2. The first part is an initial rate problem. We will write down some of the data given by the problem. We know the differential rate law is rate equals to K, the rate constant, multiplied by the concentration of NO to some order A, multiplied by the concentration of O2 to another order B. We notice that between experiments 1 and 2, the concentration of NO is the same, but the concentration of O2 is different. So we divide rate 2 by rate 1 and plug in all the known concentrations on the right side of the differential rate law. Everything cancels except the concentration of O2 to the power B. We get 3 to the power B is equal to 3, so B is equal to 1. We do the same to get the other order A. We divide rate 3 by rate 1. And finally, we get A equals to 2. Therefore, the reaction is second order in NO and first order in O2. E. The rate law is rate equals to K multiplied by NO squared times O2 concentration. F. To calculate the value of the rate constant, we can plug in the known data from any experiment into the rate law. We will pick the first one. It is important to remember that the correct unit for the rate is molar over second. Solving for K, we get 7.10 times 10 to the 3. The correct unit for K should be molar to the minus 2, second to the minus 1, because there is 1 power of concentration on top, but 3 on the bottom. For A1. Aluminum hydroxide, AlOH3, is actually a fairly insoluble compound. But if you add the solution of concentrated OH minus ions to AlOH3, it becomes soluble again. The reason is that the formation of a complex ion between Al3 plus and 6OH minus forms AlOH6 with a 3 minus charge, which is soluble. 2. Acidifying the solution means adding an acid to it. Acid solutions contains H plus ions. The H plus ions neutralize the OH minus ions, forming water. This will reduce the OH minus concentration in the AlOH6 3 minus equilibrium, and according to Le Chatelier's principle, this will shift the equilibrium to the left, decreasing the AlOH6 3 minus concentration. Hydrogen chloride gas is HCl. The reaction is between HCl and oxygen gas, which is O2. The question tells you that HCl is oxidized. When you work out the oxidation states of each atom in HCl, you will see that H has oxidation state +1, and therefore Cl is -1. And the oxidation state of the O atoms in O2 are both 0. When HCl is oxidized, the oxidation state of its atoms must go up. H, being in oxidation state +1, is the highest it can usually go. Therefore, if HCl is to be oxidized, the Cl atom must increase its oxidation state from -1 to something larger. There are a number of possible products. Cl2 is one of them because the oxidation state of the Cl atoms in Cl2 are both 0. While Cl is oxidized from -1 to 0, O2 must be reduced. Again, there are a number of possible products. The most likely oxidation state for O is -2, so H2O is a possible product. After this, we must balance the equation. There are 2 Cl on the right. We put a 2 in front of HCl. The H are balanced. Finally, to balance the O, we put a 1/2 in front of O2. We can multiply both sides by 2 to get 4 HCl plus O2 going to 2 Cl2 plus H2O. 2. If we have 3 moles of each of HCl and O2, we can determine which one is the limiting reagent by dividing each one by its stoichiometric coefficient. We see that 3/4 is less than 3, so HCl is limiting and O2 is in excess. C. Potassium oxide is K2O. When it is dissolved in water, the oxide ions undergo an acid-base reaction with water to form OH-, and the K+ ion is soluble. To balance this equation, we need a 2 in front of the K+ as well as the OH-. Phenolphthalein is an acid-base indicator. In the presence of base, it turns pink from a clear color. (5a). When an atom is ionized, an electron is removed from it. Therefore, the equation for the ionization of the F atom is F going to F plus an electron. This process requires an energy of 1681.0 kilojoules per mole. B. If you look at the location of these atoms in the periodic table, you see that F and O are on the top right of the periodic table, next to neon. In general, the ionization energy decreases going from right to left in a row in the periodic table. This is because the effective nuclear charge seen by the last electron in the F atom is greater than in the O atom, because the screening by the previous electrons becomes less complete as you fill electrons into the same n quantum number orbitals. C. Xenon is a noble gas farther down the periodic table. It should have a smaller ionization energy than F. The electron to be removed when xenon is ionized comes from an n equals to 5 orbital, but in F it comes from an n equals to 2 orbital. The 5p electron in xenon is farther away from the nucleus than the 2p electron in F, and it should be held much less tightly. D. For XeO3, we can first determine the number of lone pairs on the central Xe atom. The number of valence electrons in Xe is 8. The number of valence electrons in O is 6. Multiplied by 3 is 18. The total number of valence electrons is 26. In the Lewis structure, each O on the outside must have 8 electrons around it. This requires 24 electrons. 26 minus 24 is 2, and these must be the number of lone pair electrons on the Xe. Therefore, there is one lone pair on the xenon. After that, we start with putting a single bond between Xe and each O atom. This gives Xe 8 electrons around it, and the rest of the electrons go on as lone pairs on the 3 O atoms. Since xenon can undergo valence shell expansion, there are actually many other possible Lewis structures for XeO3. If you work out the formal charges, you'll see that each O atom has a formal charge of -1, and the formal charge on the Xe is +3. In XeF4, we can follow a similar approach. The number of valence electrons in Xe is 8. The number of valence electrons in F is 8. Multiplied by 4 is 28. The total number of valence electrons is 36. Each F atom in the Lewis structure must have 8 electrons around it. This requires 32. 36 minus 32 is 4. These are the number of lone pair electrons around the Xe. We put 2 lone pairs on the xenon, and we start with a single bond between the xenon and each F atom. There are now 12 electrons around the Xe. The remaining 24 electrons out of the 36 total can now go on to the 4 F atoms, with 3 lone pairs for each. E. We can use VSEPR to figure out the geometry of the XeO3 molecule. From the Lewis structure of XeO3, we see that there are 3 bonds around Xe. Each one counts for 1 electron domain. In addition, there is also a lone pair, which also counts for 1 electron domain. Therefore, there are 4 electron domains around the central Xe atom. The proper VSEPR template is tetrahedral. we put the 3 F atoms on this template, they occupy 3 of the 4 positions. The molecular geometry is given by the positions of the atoms because we don't see the lone pair. Therefore, the correct geometry is trigonal pyramidal. For XEF4, from the Lewis structure above, we see that there are 4 single bonds and 2 lone pairs around the Xe atom. Therefore, there are 6 electron domains around the central atom, and the correct VS-EPR template is octahedral. For this, we must have a sp3d2 hybridization. F. XeO3 should be polar. Because each OXe bond is polar, O being more electronegative than Xe. The dipole moment of each OXe bond pulls electron density towards the O atom. The net result of these is that the electron density is concentrated on the side of the molecule with the 3 oxygens. (6a). We draw the 2 structures here. Here each corner without an atom label is a carbon atom. In the pyridine molecule, one position is special. The N atom is bonded to the 2 neighboring carbon atoms, and the CN bond is polar because N is more electronegative than carbon. Therefore, pyridine is a polar molecule. On the other hand, benzene is nonpolar because the CC bond is nonpolar and the benzene molecule is completely symmetric. If there were any polar bonds in benzene, the dipole moments would have cancelled each other out completely. Since pyridine is polar, it tends to dissolve in a polar solvent like water. Benzene is nonpolar and does not dissolve in water. B. We reproduce the structures of these two molecules. In dimethyl ether, the CO bonds are polar, with electron density higher on the oxygen side. If you determine the VS-EPR geometry of dimethyl ether around the oxygen atom, you see that is actually bent. With the two CO bonds being polar, the molecule has a non-zero dipole moment, so dimethyl ether is a polar molecule. When we look at ethanol, we see that the CO and the OH bonds are also polar. Looking at the VS-EPR geometry of ethanol around the oxygen atom, we see that ethanol is also a polar molecule for the same reason as dimethyl ether. But since the hydrogen in ethanol is bonded to an O atom, ethanol can actually form hydrogen bonds, whereas dimethyl ether cannot. The additional ability of ethanol to form hydrogen bonds among themselves make it have a higher boiling point. C. The SO2 molecule has a Lewis structure like this. When SO2 forms a solid, it forms a molecular solid. What is holding the solid together are dispersion forces. On the other hand, when SiO2 forms a solid, it forms a network solid. Each Si likes to form 4 bonds, and each O wants 2 bonds. The best way to satisfy their valences is for each Si to be bonded to 4 oxygens, and each oxygen bonded to 2 silicons. Therefore, SiO2 should have a much higher melting point. D. The Cl2 molecule is nonpolar. The only intermolecular forces among Cl2 molecules are London dispersion forces. On the other hand, the HCl molecule is polar, so in addition to dispersion forces, there are also dipole-dipole interactions among HCl molecules. But the problem tells you that Cl2 actually has a higher boiling point than HCl. This must mean that while HCl has dipole-dipole forces between them in addition to dispersion forces, the dispersion forces among Cl2 molecules are actually stronger. In general, the larger the molecule, the stronger the dispersion forces among them. So Cl2, being larger and having more electrons, can have significantly stronger dispersion forces than HCl.